Hi everyone, I am Professor N.K. Pandey from Department of Physics, University of Lucknow. Today, I am going to discuss one of the topics from the quantum mechanics, that is the Compton effect. Now, let us go back to somewhat background. Max Planck proposed, while studying the emission coming out from hot bodies, that these emissions were coming out in the form of small packets or bundles of energy called quanta. He also proposed that this radiation, although came out in the form of quanta, but they propagated as continuous electromagnetic waves. Einstein said that no doubt these radiations coming out from the hot bodies came out in the form of quanta, but he also said that they propagated as quanta as well. Now, these quanta had no rest mass, but they did carry momentum. And therefore, because they had the momentum, therefore they could make collision with other particles. And hence, we can say, to study the Compton effect, we have a takeaway from the quantum theory, and that is the photons behave like particles except for the absence of any rest mass. Hence, collisions between photons and electrons should be treated as billiard ball collisions. What is Compton effect? Compton effect is the inelastic scattering of a photon by a quasi-free charged particle, usually an electron. Now here is the Compton effect shown figuratively. We have an incoming X-ray photon making collision with an electron. The X-ray is going in this direction and the electron by impact is going in this direction. Now, the energy of the X-ray photon is in the range of 15 to 20 kilo electron volt. This energy is very large compared to the binding energy of the atomic electron, which is of the order of couple of electron volt. So, for the X-ray photon coming, the electrons could be treated as almost being free, hence the quasi-free charged particles we are calling them. Now, this scattering results in a decrease in energy, that is the increase in the wavelength of the photon. This scattered radiation has both the original as well as the increased wavelength. The presence of the original wavelength may be explained on the basis of electromagnetic theory, but certainly the presence of increased wavelength can't be explained on the basis of electromagnetic wave theory. Now, to explain the presence of original wavelength through electromagnetic theory, we can say that the incoming radiation is absorbed by the atom. The atom goes to the excited state, and when it de-excites, it emits the same radiation, and therefore the incoming photon and the radiated photon by de-excitation will certainly have the same wavelength. Now, part of the photon energy is transferred to the electron. Now here, we have shown in the figure the collision between an X-ray photon and an electron, which here is assumed to be at rest, initially at rest. So we have the incident photon, we have the target electron, and this is the scattered photon. We can see that this has a wavelength lambda and this has a larger wavelength lambda dash. And this is the direction at an angle theta to the original direction, the scattered electron, and the scattered photon is at an angle phi to the initial direction. In the collision, the photon loses as much energy as the kinetic energy gained by the electron. In the collision, momentum is conserved in each of the two mutually perpendicular directions. Now here it may be understood very clearly that two separate photons are involved. One is the initial photon that has a frequency nu, and one is the scattered photon that has the frequency nu dash. That is, incident photon has wavelength lambda and the scattered photon has wavelength lambda dash. Now, let us go for the calculation. Loss in the photon energy is equal to gain in kinetic energy. So h nu is the energy of the incident photon and h nu dash is the energy of the scattered photon, and T is the kinetic energy gained by the electron. So the total energy may also be written as, by the relativistic formula, E is equal to square root m naught square c power 4 plus p square c square. M naught is the rest mass energy and p is the momentum. Since the photon, as I have said earlier, has no rest mass, its total energy may be given by E is equal to pc because m naught is equal to 0. And therefore, we have p, that is the momentum carried by the photon, E upon c, that is h nu upon c. Now, momentum must be conserved in all directions. The initial photon momentum is h nu by c and the final momentum carried by the photon is h nu dash by c. Now, let us apply the conservation of momentum. Now, here we again quote the figure for convenience. We have the total momentum initially along the incident direction, and that is h nu by c was the momentum of the incident photon. The electron did not have any momentum, so h nu plus c, h nu by c plus 0 was the initial momentum along the, let us say this one is the x direction. And then the final momentum will be h nu dash by c cos phi plus p is the momentum carried by the electron, so p cos theta. And the total momentum perpendicular to this direction, that is, consider this one as y direction, then initial momentum along this was 0 and the final momentum is the component of this one along this and the component of this momentum carried by the electron along this. So we have 0 equal to h nu dash by c sine phi minus p sine theta. Now multiply these equations by c and then we have these two expressions. Pc cos theta is equal to h nu minus h nu dash cos phi and Pc sine theta is equal to h nu dash sine phi. Square and add them together and we will get this particular expression. P square c square is equal to h nu whole square minus 2 h nu dash cos phi plus h nu dash whole square. Now E is also equal to T plus m naught c square. So E is equal to square root m naught square c power 4 plus p square c square. So to equate the two, we can write it like this: T plus m naught c square, this way square, then if we square this, then this becomes equal to this. So T plus m naught c square whole square is equal to m naught square c power 4 plus p square c square. When we square this one, then m naught square c power 4 will get cancelled and we will be left with this particular expression, that is p square c square, that is this one, is equal to t square plus twice m naught c square plus t. But t is equal to h nu minus h nu dash as we have seen earlier. Therefore, p square c square can be written as this placed over here and expanded, that is p square c square is equal to h nu whole square minus twice h nu into h nu dash plus h nu dash whole square plus twice m naught c square h nu minus h nu dash. So a little bit of left and right calculation will give us the final expression as lambda dash minus lambda is equal to h by m naught c 1 minus cos phi. Now lambda dash is the wavelength of the scattered photon, lambda is the wavelength of the incoming photon, m naught is the mass of the electron, h is the Planck's constant, c is the speed of light, and phi is the angle of scattering. Now let us see that we change the value of phi from here, that is the angle of scattering, and we have different values of the change in wavelength. We have, if the angle is 0, then the delta lambda will be 0, because if cos this 1 minus 1 is equal to 0, so delta lambda is equal to 0. Similarly, if phi is equal to 45 degree, then one wavelength will be the difference in wavelength will be approximately this one. You increase the angle of scattering and the difference in wavelength will increase. You increase up to 135 degree and the difference again becomes larger. And of course, if we make phi is equal to 180 degree, then cos phi is equal to -1. So 1 minus -1, that is, this becomes +2. So 2h by m naught c. So what we can say is that as the angle of scattering changes, so does the change in wavelength. Now let us see some salient results of the Compton effect that we have just seen. Number one, change in wavelength is independent of the wavelength used. That is, lambda was the wavelength of the incident photon. H by m naught c does not, or 1 minus cos phi does not have lambda. So change in wavelength is independent of the wavelength used. H by m naught c is called the Compton wavelength, which for an electron is equal to 0.024 angstrom. Now, the presence of higher wavelength is now explained over here, as we have seen from the formula lambda, and you can see from here lambda dash minus lambda is equal to h by m naught c 1 minus cos phi. This we have got by applying the conservation of momentum and taking the photon as a particle, and conservation of momentum has been applied. So what do we see? That change in wavelength is independent of wavelength used. The presence of higher wavelength is explained over here. And how do we explain the presence of original wavelength? That we will see little bit later. And the maximum change in wavelength for phi is equal to 180 degree is twice the Compton wavelength, that is 0.048 angstrom. Now, Compton found that some X-rays experienced no wavelength shift despite being scattered through large angles. In each of these cases, the photon failed to eject an electron. Thus, the magnitude of the shift is related not to the Compton wavelength of the electron, but to the Compton wavelength of the entire atom, which can be 10,000 times smaller. Now, this is known as coherent scattering of the entire atom, since the atom remains intact, gaining no internal excitation. Now, you can see from here, from the formula itself that we have seen earlier, that if the photon is making collision with the whole atom as such, then the mass m naught over here should be taken as the mass of the atom as a whole. In that case, this mass is many times greater than the mass of the electron. And therefore, this change in wavelength will become negligible, and hence we can say that the wavelength of the scattered photon will be same as the wavelength of the incident photon. And of course, this explains the presence of the original wavelength in the scattered radiation. So thus, we have been able to establish that the wavelength change is there through the quantum theory, and the original wavelength is also present in the scattered radiation. Now, at a time, early 1920s, when the particle, that is photon, nature of light suggested by the photoelectric effect was still being debated, the Compton experiment in 1923 gave clear and independent evidence of particle-like behavior of photons. That was the greatest achievement of this Compton experiment. And Compton was awarded the Nobel Prize in 1927 for the discovery of the effect named after him, Compton effect. Thank you very much for your kind attention.